In our previous lecture, we have seen that for a single cylinder engine, the turning moment on the crankshaft varies quite substantially. That is, if we plot the turning moment for a whole cycle, taking a 4-stroke cycle engine, so we have seen that it will be something like this, whose average value will be so this is the turning moment m, and this is the average value of this. How to find out? First, let us find out this is one cycle. And in this particular case, the crank rotation to complete one cycle will be 2 rotations, that is angle theta will go to an angle 4 pi. Now, the total work done by the engine in one cycle is what? Because if it goes by, it rotates, the crankshaft is rotated by an infinitesimal angle d theta when turning moment on it is m, then the work done by the engine is m to d theta. So therefore, in whole cycle, the total amount of energy which is generated can be written as in this particular case, that means for 2-stroke cycle, E will be equal to 0 to 2 pi m d theta, and for 4-stroke cycle engine, energy will be so this is the amount of energy generated in every cycle. And obviously, in steady state, we assume the same amount of energy is utilized, so that there is no accumulation of energy in the engine continuously changing its speed. In case of starting, either it increases, or when it is less than the power utilized at the output end, then it will gradually go down. So in steady state operation, what we have, the resisting torque, which is constant, we have assumed in this particular situation, it must be equal to the value such a way that total work consumed by the load is same as the total energy produced in every cycle. So the load m is same as m average, which is nothing but the energy produced per cycle divided by 4 pi in case of 4-stroke cycles as shown here. That means we can write it like this. So once we know the turning moment diagram, it is possible for us to find out the average moment, or which happens to be the load or the resisting moment. Now we find that if we draw this resistance or resisting moment, then I think we find that if some places this is above this resistance. In some cases, driving torque is less than. So here what will happen? Energy will be added to the system, so the kinetic energy will go up till point B, after which the driving moment becomes less than the resisting moment. So energy is depleted and kinetic energy goes down up to a point C, where again your driving moment becomes more. That means it starts accelerating the system, adding energy till the point say D, where again the driving moment becomes less than the resistance, and so energy is depleted, reducing the speed. Again it goes back to point A. So here we find that energy at A is say EA. Energy means obviously mechanical energy of the system, that is the kinetic energy. So at point B, the energy will be whatever energy we had at point A plus the energy added this is the amount of energy which is added in that first lobe, which is indicated as plus. Similarly, energy at point C will be E of B plus theta B to theta C m minus mr d theta. But remember, m minus mr is a negative quantity, and so actually it is going to be a negative quantity. Similarly, at point ED, the energy ED is energy at point C plus and we then finally come back to A, which is again so this is just an example. It can have many more lobes and different, because remember this is a case of a single cylinder engine. If we have more than one cylinder, then what will happen? The turning moment diagram of one cylinder and the turning moment diagram of the other cylinder, they will have to be superimposed with suitable lag. In case of two-stroke or two engines, obviously they will be separated by 2 pi angle, and so then the final turning moment will be a superimposition of data. If there are more number of cylinders, then the turning moment of each and every cylinder will have to be added by suitably phasing them, and the final turning moment diagram can be having many more loops than what we have here with only one cylinder. Now let's say, let E1 be the maximum energy. Amongst all this, of course, you have to see that energy can be maximum in any of these points, here or here and so on. Similarly, energy can be minimum also, either here or here, like that. So therefore, one of these must be the highest and one of these will be the lowest. It cannot be anywhere in between, and E2 be the minimum. The corresponding angles be theta 1 and theta 2. So, what will be the difference between the maximum kinetic energy of the system and the minimum kinetic energy? What we call that maximum energy, kinetic energy fluctuation, that is the difference between the maximum and minimum values of the kinetic energy during the whole cycle, will be nothing but now the quantity, now if this maximum fluctuation, that means the difference between the maximum and minimum values of the kinetic energy, what we call delta Ke max. If we divide this by the energy input per cycle as defined by this, is called coefficient of energy fluctuation. Now, what is this fluctuation, this maximum and minimum kinetic energy? Now, obviously, we can always write, if the, let I be the equivalent moment of inertia of the whole system assumed to be mounted on the crankshaft. So, at any instant, the kinetic energy of the whole system can be now represented by this quantity. So, E max is nothing but the maximum kinetic energy of the whole system, that is half I omega max square, or omega max is the maximum speed of the crankshaft. Similarly, E mean will be half I omega mean square. So, therefore, delta Ke max is nothing but half I omega max square it is nothing but the difference between the maximum and minimum kinetic energy. This can be written in this form, I into omega max plus omega mean by 2 into omega max minus omega mean. Now, what we can do, this, there is a fluctuation of speed obviously. What we can do, this omega max plus omega mean, their average in most cases, since the difference is very small, can be considered to be the omega average. So, this can be approximately written as omega average or the average running speed of the engine. So, we can write this as I omega average square into omega max minus omega mean by omega average. And this is I. Where the maximum variation in the speed divided by the average speed is called the coefficient of fluctuation of speed. This is an important parameter which has to be prescribed depending on the situation or the kind of machine we are driving with the engine. So therefore, we find that if Ks is prescribed, running speed is known, which is the design speed, turning moment diagram is known, then in the steady state we can find out what must be the equivalent moment of inertia of the whole system. Generally, what is done that the system's inertia is not enough, and to provide or to make the system running smoothly, we increase the value of I substantially. How can it be done? The easiest way of doing it is that we attach a heavy wheel to the crankshaft. Normally that is called flywheel because its function apparently is not seen very clearly, but what it does, it provides a substantial amount of magnitude to this moment of inertia attached to the crankshaft, and for a given fluctuation of energy it produces much less fluctuation in the speed, or in other words the engine runs smoothly. So in most cases you can say is approximately equal to the flywheel moment of inertia, because engines, connecting rod, etc., and the balancing masses which are added, they have inertia, but the real contribution to I comes from the flywheel which is attached to the connecting rod. And therefore we can now find out that approximately we need a flywheel whose order of magnitude is found out from maximum fluctuation of energy divided by omega average square into coefficient of fluctuation. So this is the way or technique by which we can have very small fluctuation of speed by having very heavy flywheel. And therefore, as you have seen, in most engines we attach a heavy flywheel to the connecting rod. As I mentioned just now, that the value of Ks depends on the kind of situation or the kind of function we are achieving. So I will just give you some idea about the magnitude of Ks in various situations. This table shows the permissible recommended values of the coefficient of fluctuation of speed. In case of shearing machines, pumps, the accuracy required is much less, and value of Ks is in that range, 1 by 5 to 1 by 30. In machine tools of different types, textile machines and such types of situations, Ks can be permitted to be within 1 by 40 to 1 by 50. In case of electric generator or generating set, the recommended variation of speed has to be 0.01 to 1/3 of that, and automobiles or auto engines, the recommended value of Ks is this, and aircraft engines of course will have to be far more accurate, and there the speed fluctuation which is permitted is the minimum. Now let us consider just how to use this. One example let us solve. Let us take the case of an example of an engine. So the engine runs at RPM, 800 RPM. Permissible value of the fluctuation of speed is 2%, and the turning moment diagram has been given. The turning moment in Newton meters and theta in radians. This is one cycle. Now, here what has been done, this point A, this is point B, this is point C, point D, point E, F, G, H, which is same as A. Now, here of course you see that it is again becoming negative, that does not matter. So, here the area, when you plot it both in centimeter and centimeter in this direction, this area is found to be minus 0.5 centimeter square. This is plus 1.2 centimeter square. This is minus 0.95 centimeter square. This is plus 1.45 centimeter square. This area is minus 0.85 centimeter square. This area is plus 0.71 centimeter square, and this is say minus 1.06 centimeter square. So we plot this. That means here actually we will find scale will be 1 centimeter is equal to 30 degrees, and here 1 centimeter will be equivalent to 7,000 Newton meter. That is the scale we have used, and using these scales, these are the areas we measure by planimeter. Next, what we do, let us find out what is the maximum kinetic energy and minimum kinetic energy, as we have been doing. How do we do? We start with A, say energy at A point is EA, energy at point B is EA minus 0.5. We need not convert this centimeter square into energy now. We can do it at a final thing, because everywhere if we just keep on in terms of the area, we will be able to identify the maximum and minimum, and then we will convert to the real energy units. So the energy at this location is EA minus equivalent of energy, which is this. EC will be EB plus 1.2, which is effectively EA plus 0.7. E at D will be E at C minus 0.95, which means it will be E at A minus 0.25. E at E is E at D plus 1.45, which is same as EA plus 1.2. E at point F is equal to E at point E minus 0.85, which is same as EA plus 0.35. And E at G is E at F plus 0.71, which is equal to E at A plus 1.06, and E at H is equal to E at G minus 1.06. So we come back to a point at point H, the energy should be equal to EA. Now let us see out of this which is the maximum and which is the minimum. So it is not difficult to identify the maximum and minimum energy location. Say we can compare all the values EA, this, we find that this is E maximum and we can find this as the E minimum. So the maximum fluctuation of energy which is nothing but E max minus E min, which is equal to or equivalent to, rather we can say, (1.7 centimeters). Now how much 1 centimeter square represent? Now torque into theta, torque in Newton meter into theta in radians is joule. So 1 centimeter square is equivalent to 7,000, and 1 centimeter is 30 degrees, in radians it is pi by 6, so many joule, which is 3, 6, 7, 0. This is the scale. So here if you multiply by this, this is in joules, it is which is equal to 6240 joules. Now our Ks has been specified as 0.02 and omega average, which we should be able to find out from this, 800 RPM, which is 800 into 2 pi by 60 radian per second, which is 33.8 radian. So therefore we utilize the formula derived that moment of inertia of the flywheel will be approximately equal to, neglecting the inertia of the other parts of the machine or the engine, and this is equal to 6240, and so many. What will be the unit for this? Kg meters. If we follow SI unit, everywhere we will get straight value. And finally, this is equal to so if we put or if we attach a flywheel with this much of moment of inertia, then the fluctuation of speed will definitely be contained within 2% when the engine runs at 800 rpm and when the fluctuation of energy or the turning moment diagram of this multi-cylinder engine is as specified. Let us now take up another example which is of the other type. If you remember that we mentioned that there can be two types of situation. In one case, the driving torque fluctuates and the load torque is uniform, just now as we have done. Another common example of fluctuation we find when you use machines like punching or shearing machines, where the load fluctuates substantially and the driving, which is done normally with the help of the motor, is uniform. So, the basic mechanism involved in a punching machine is also a slider crank mechanism. This is the crank which is rotating, and during this rotation you find that it at a particular location which is indicated like this, the punch just touches the plate, it has to pierce, and with little bit more rotation of the crank, piercing is completed. So therefore, only during this period there is load or work done. Rest of the portion of the operation in one cycle is absolutely free. There is hardly any torque. That means if we plot here, one cycle obviously is one rotation, so it will be phi, and moment let us see. So the moment except the point when it touches this, the resistance will be something like this. And the amount of energy which is consumed here, which is given by this area, that same amount of energy must be supplied by the motor during one rotation. So the supply torque which is constant, which will be this, and this is MR. So here what we find, that during this period, say theta 1 and theta 2, the energy at here, this area must be equal to the area this and this. So what we can do here, that maximum fluctuation of energy can be written as if you call this total amount of energy as E minus the amount of energy here, which you can call as E prime. That means this is E. So this is the fluctuation. And as you can see very easily, now I think without going into the details of operation of this, we will make some very approximate approach. Approximate approach will be that how much is E prime. E prime you can easily find out from here that the amount of energy here will be just in proportion to the amount of energy in the whole cycle and this particular angle or the rotation. So it can be written as total energy of the whole cycle is E, and what fraction will be here? It will be theta 2 minus theta 1 divided by 2 pi. Approximately you can consider this, or this is nothing but the E 1 minus the rotation of the crank during which punching operation is accomplished. Approximately, of course, remember. And this will be obviously again equal to half moment of inertia if we consider that it is the flywheel which is the predominant moment of inertia, then IF and we have seen that this can be written as IF omega average square. So in this case, rather than going into the details of where the intersection points are and finding in a complicated way, a very approximate method for finding out the fluctuation of energy in case of punching machines can be taken as this. Now let us take up a particular problem. The problem I am taking up is not only just to solve a numerical problem, but also to demonstrate something which will be also very important, as you will realize. Let us consider a case where punch hole diameter is equal to 3.8 centimeter, hole depth is 3.2 centimeters, work done in punching is equal to 600 joules per centimeter square of sheared area. Stroke of the punch is equal to 10.2 centimeters. Thickness of the plate is not needed, which is same as the length of the hole or depth of hole. 6 holes per minute, and Ks is told that it can vary up to 20%, because it's a punching machine. As you have seen, it can be even as low as 1/5 from the previous table. So let us find out the required flywheel to be put on the crankshaft directly, so that the coefficient of fluctuation of speed can be kept within 20% with this situation. Now energy required per punch or per cycle will be how much? It will be the shared area, which is nothing but pi d into T. Into 600 joule, and this, if you calculate, you will get 22,920 joule. That means to punch each hole, we will require so much of energy. Now, theta 2 minus theta 1 by 2 pi, how much is this? Now this again, we can do a more accurate analysis we can do by actually drawing the whole thing, drawing sheet. But otherwise also we can consider the movement of this whole thing to be linear, that means the speed and displacement bearing a linear relationship. If we do that, then the amount of displacement which is required for the punch during punching is T, that is the thickness, and for total length of movement of this, which is twice this stroke, 2s, for that movement is 2 pi. So therefore, this will be very crudely we can write as T by 2a, and that is in our case 3.2, and this is stroke length is 10.2, so 20.4. So this is the value here. So fluctuation of maximum fluctuation of energy will be approximately equal to energy E, which is 22,920 into 1 minus and this must be equal to the moment of inertia of the flywheel, average omega square. Average omega we can find out because it is 6 holes per minute, that means 6 rotations of the crankshaft per minute, that is 6 into 2 pi by 60, so many radians per second square, into Ks, which is 0.2. And from this, if we calculate the required flywheel moment of inertia, will be and this will be using SI unit, we will get this directly in kg per kg meter square. And I think I have calculated it comes to something like so you see that we require a huge flywheel to maintain the speed even when we are allowing it to vary by 20%. So which is obviously not a feasible solution. Now this is solved in this manner, that if we have this crankshaft and this is a punch. Now rather than directly attaching the flywheel with this, we use a gearing system and we attach the flywheel on idling shaft which is fixed. And omega of flywheel by omega of the crankshaft is equal to say n, depending on the gear ratio. Now what happens if If be the moment of inertia of the flywheel, the system energy, system kinetic energy then becomes half If into n into omega square. So therefore, maximum fluctuation of kinetic energy can be written as half If n square into omega max square minus omega mean square. So effectively what we get, If can be written as maximum fluctuation of energy by omega average square into n square into k. So for example, in this particular case, if we put the flywheel on an idling shaft which is connected to the crankshaft by a gear train which gives a ratio of say 10, moment it happens, our moment of inertia of the flywheel required becomes something. That means if you put a rim weighing 2.5 tons at a radius of m, which is quite possible, flywheels are big, then I think your permitted coefficient of fluctuation of speed will be maintained. If you make the speed little bit higher, say if you want to make it say 20 ratio, then the whole thing will be still half. It will be only 1.2 ton of a rim, which is quite possible flywheel and at a radius of meter. So this is what I wanted to demonstrate, that where you find connecting the flywheel directly on the operational shaft requires or makes the requirement of the moment of inertia of the flywheel to be very heavy. What we can do, we can use an idling shaft on which the flywheel is mounted and which is connected to the main shaft or crankshaft through a gearing system or a transmission system, where that means what effectively we are doing, we are making this real source of kinetic energy to rotate at a higher level of speed. That will make the requirement of the inertia to be lower and the machine will be much lighter. I think there are more complicated cases and problems which we will not go into it. Only this thing will be enough for you to remember that the whole system or the whole analysis is very approximate, because a higher level of accuracy or better or more accurate analysis of this problem really does not mean much, because our choice of case is a very ad hoc thing. Okay, that we allow only 2% variation, etc. So that of course is very ad hoc, and therefore making a very accurate analysis of the whole matter is really not required. Only thing you have to keep in mind that the fluctuation of speed in its operation is not allowed to go beyond certain limit, and this as a result what is doing, the whole system is running with a much uniform speed. That means again it is nothing but smoothening of operation. As you have seen that removing the unbalanced dynamic forces, we make the vibration of the system less and the system runs smoothly. This is another way to do it, that where the actual operational speed also is allowed to maintain a uniform value as much as possible, and this is the smoothening of the operation.